But let's look now at what a partial derivative is. The way we write partial derivatives involve the Greek letter delta. So firstly, let's say that we've got z as a function of two variables. Now that's imperative, you've got more than one variable to do partial derivatives. You've got at least two. You can have 3, 4, multiple, but you've got to have at least two. So we've got, to do partial derivatives, you need a function of two variables. So we've got z as a function of both x and y. To write partial derivative of f with respect to x, so we say partial, you use the word partial, df dx. So that's what we say when we see that. So when you look at that in written form, say partial df dx. The word partial means that we've got more than this variable, we've got other variables as well. What is this? So partial df dx is df dx with y constant. So if you've got a function of both x and y, we just keep y constant and we just find df dx. Example, let's go back to f of x, y, our original one, is equal to 4 minus x squared minus y squared, which I introduced in the previous video. Then partial df dx is find the derivative with y constant. So this is going to be treated just like that 4 as a constant. So derivative of constant 0, derivative of minus x squared with respect to x is minus 2x, and the derivative of a constant is 0. So most of you won't need to put those two zeros, and we'll just say that's minus 2x. What's the partial derivative of f with respect to y is, we find df dy with x constant. So using the same example here, partial df dy is equal to, go back to our function, x is constant, so derivative of constant 0, derivative of another constant 0, so that'll be just equal to minus 2y. So that's partial derivatives. Now, what are they and what do we use them for? Let's go back to our graph of f of x, y is, or we can say that's equal to z, is equal to 4 minus x squared minus y squared. So previous video we said that was a surface, and that surface looked a little bit like that. So this is the graph of z equals 4 minus x squared minus y squared. And from above there we've got partial derivative of df dx is equal to minus 2x. So let's write that in. So partial derivative, so this is f of x, y. Is equal to minus 2x, and partial df dy is equal to minus 2y. Now what does that mean? Alright, don't forget partial derivative of the function with respect to x, we're saying y is constant. So if we look everywhere along, let's look at this line here, everywhere along here y is constant. Okay, so y would be negative 0.8. Okay, so y come out negative 0.8 out to here. So we go from there out to roughly around about there, which is negative 0.8. So y is constant everywhere along there. So this gives us the gradient at any point along that line on the curve. So this is the gradient function for that line. In other words, delta partial df dx is the gradient in the x direction. This is going in the x direction because we've already said that the x-axis is going to be going straight underneath that line there. This, let's do it in another colour here. This one here, so partial df dy is the gradient in the y direction. So if we look at, say, this line here, everywhere along that line x is equal to negative 0.5, everywhere along that blue line, if that's straight above there. Negative 0.5 for x is there, and so everywhere along there x is negative 0.5, so everywhere along this line here we've got x is equal to negative 0.5, so x is constant, so it is the gradient, if you like, at any point along that line. In particular, at this point here, where those two intersect, at this point here, so at, now what is that point? X is equal to negative 0.5, y is equal to negative 0.8, and z will be equal to 3.11 if you substitute in that and square it, substitute that and square it, and take it away from 4, you'll get z is equal to 3.11. So at that point, the gradient going in this direction will be equal to minus 2 times the x value. So partial df dx, we've already said, is the gradient in the x direction, so the gradient along that line there is equal to minus 2 times negative 0.5, which will be equal to positive 1. So the gradient everywhere along that line, no, the gradient at that particular point in this direction, going that way to that way, that gradient will be equal to 1. If we want to find the gradient at this point here, going in this direction, so at this point, let's do another colour there, so partial df dy would be, it was minus 2y, so minus 2 times the y value at that point is negative 0.8, so that'll be 1.6. So the gradient here, going in that direction, will be equal to 1.6. The gradient in this direction, going from there to there, is equal to 1. And that looks right, because it looks like along that line it is actually still climbing going up there. When you go in this direction, when you go in the blue direction here, the purple line there is the tangent, and it'll have a gradient of 1.6. So partial derivatives gives us gradient in particular directions, and partial df dx is the gradient in the x direction, partial df dy is the gradient in the y direction.